So, welcome to my presentation. Yeah, the title was already told. So I'm concerned with passenger comfort, basically, and especially with the reduction of vibrations. And for the PTS, that's the passenger transportation system. Exactly. There it is. Yeah, in this paper, I will show them how or parts of how I modeled it. Before we begin, I will start to just a short introduction. So I studied control engineering at the University of Stuttgart, and my PhD topic is develop a damping concept for the PTS. And I'm working closely together with Thomas Ehrl, who's the head of the research, or probably you know him better. Anyway, so now I'm gonna come to the outlook. So first I'm gonna introduce shortly my institute, so the Institute of System Dynamics of the University of Stuttgart. Then I will motivate my talk. Then I will shortly show the system, that's the rope-free passenger transportation system, and talk shortly about the vibrations in this context. Then I will go into the or how we derived the model for this paper, and show a simplified version of this of the model we used for this paper, and then I will conclude and show you further steps. So let's start with the Institute of System Dynamics. So their main topic is control engineering. There's methods like modeling or optimization also, and analysis and synthesis of controller. But a second important topic is the application of these methods in a broad variant of systems. And we work together, besides a lot of publicly funded projects, we work together with a lot of companies and also developed, for example, for a ladder, fire truck ladder, a damping concept. Exactly. So exactly. So now let me motivate my talk. So a few years ago, I was doing my bachelor thesis, and I to get to the fastest way to get to my supervisor was so one special lift at my university. Sadly, it doesn't look half as good as this lift. It was built in the 70s as the building. And every time when I was riding in it, I had not that much of a comfortable feeling because it vibrated to an extent where I wasn't even sure if it was safe to ride in it, especially at every stop. So to not have this for the PTS, the University of Stuttgart, and ThyssenKrupp elevator from the partner or a project-based partnership, to develop a damping concept and so to achieve a good passenger comfort when you ride with the PTS. So let's talk about the PTS. The main difference is that it has no rope and rather uses a linear motor to get the driving force. It consists of a sledge which holds the passive elements of the linear motor, the cabin and the mounting frame. The mounting frame basically supports the cabin. The advantages of this system is that, as you can already see, it can drive, or it's possible to drive horizontally, and also multiple shafts, multiple cabins can travel in a single shaft. And as you can see, the design is different than from conventional lifts. So we will have to develop a new damping concept for these lifts. And we want to damp some vibrations, and I will talk now about the vibrations we want to damp. And as told last year at this conference, vibrations are one of the key factors which reduce the passenger comfort. and therefore we need to develop a concept to damp them. The vibrations we're concerned with are basically the same as the vibrations of a normal lift, so rail imperfections and so on. What you don't get is the rope, because it doesn't have a rope. But what you get in addition is the linear motor, which induces very high frequent vibrations. And the rest of the vibrations, so the imperfections in the rail and so on, depend highly on the traveling speed of the elevator. And therefore they are low to mid-range, but not as high range, not as high frequent as the vibrations of the linear motor. It is high frequent vibrations, or can be effectively damped by passive elements. And in the low and mid frequency, the passive elements don't work as good, but you can use active elements. So the aim is to find a combination of active and passive damping elements to damp in a broad range of vibrations. So now let's. So why do we need a model in this context? So there are very many applications for a model in control engineering. One would be to simulate the dynamic behavior of a system before you can measure anything. And also you can add to this model active components, as we see before, and design a control algorithm and test it before you run the simulations. So we use mathematical methods to derive a model of the PTS in this paper in order to describe the behavior of the real system. And so now it's the question, what methods did we use? So we used rigid multi-body systems. So we have here our PTS again, and divided this PTS into 3 bodies, basically. So in this 3 rigid bodies in this system, it's easy. It's the sledge, mounting frame, and the cabin, and introduced some coupling elements or like joints or binding elements like spring and dampers, the other way around, sorry. And for example, the parameters of the spring and dampers then describe basically the dynamic behavior of the system, and we try to match them as close as possible. It is important to know that these parameters for the spring and dampers have to be found through additional simulations, or other parameters can be get out of the CID files, but it is always important. If we want to match the behavior, we need additional measurements from the real system, so we can actually validate the model we have derived. So now let's go to the model for this paper. This model is a simplified version of the 3-body system. We only take 2 bodies, so the cabin and the bucket, and neglect the sledge. So we don't have any vertical movement in this case, which is the desired movement, and only look at the vibration that are conveyed through this connection point between mounting frame and sledge, and look at the vibration inside the cabin. Beneath the cabin are some arbitrary actuator elements, which could be anything. It could be passive elements or some active component, which is not that important for this paper. And I also reduced the model to a 2D version, so we have 2 translatory movements in each in the cabin and the bucket, and then a rotation around the y-axis, which are the degrees of freedoms. So this system can be used for a lot of stuff, but we used it here to make a simple simulation. So we start at the equilibrium point, so the forces of the actuators and additional torque here is chosen such that the gravitational forces are compensated. So if we have no disturbance at all, this will stay in this position. And then I introduced a disturbance, which represents a plus minus 3 millimeter deviation or periodic deviation over 10 meters, that's 2 rail lengths. And recalculated this into torques that attack at the connection point between mounting frame and sledge. So the mounting frame moves and will move this point, and this is conveyed through this spring and damper elements here into the mounting frame. And we will look at the absolute acceleration inside of the cabin and specifically at the center of the gravity. So let's look at the simulation again. So on top we have, I represented the deflection of the rail over 10 meter length and the plus minus 3 millimeter, so it's a sinus basically. And on the bottom we see the vibration inside of the cabin. I forgot to tell you that the traveling speed of the PTS is assumed to be 10 meters per second. That's needed for the calculation of the disturbance, torque, and force. But again, what we can see over time plotted on the bottom is the acceleration, absolute value of the acceleration inside of the cabin. And this acceleration exceeds the 10 milli-G border. So we see here that for this simple simulation, we will need a further damping concept in order to achieve our goals. So this already brings me to the end of the presentation. So let me conclude. In this paper, I derived a model of the PTS and also showed some of the basic steps which have to be undertaken if you model it with rigid multi-body systems. I performed a simple simulation with this model. This simulation showed that it is necessary to develop a further damping concept for this, and thus we need the further steps, so include some actuator dynamics inside of the model. One next important step is to validate this model, but probably not this model, but the 3D model of it, 3-dimensional model of it on the real system, and use then this model to design the active damper elements, so the actuator dynamics above, and calculate what we need. And also the main point is to later use this model to derive the controller for this, or the optimal controller for this actuators or damping system. So we hopefully seen that it is important to have a model to actually derive all of these damping concepts. So.